January 1942. Newport News Shipbuilding and Dry Dock Company, Hampton Roads, Virginia. The water is black. The air smells like rust, diesel, and burning metal. Inside Dry Dock Number 9, the skeleton of USS Thomas Jefferson lies half-finished. Steel frames rise from the concrete floor like the ribs of something that hasn't yet learned to breathe. The thermometer reads 38 degrees Fahrenheit. It's 4:47 in the morning. This is the American shipbuilding industry at war. 3 weeks earlier, President Roosevelt gave the order, build 200 Liberty ships. Not next year, this year. Cargo vessels, 441 feet long, built to carry ammunition, grain, fuel, and soldiers across the Atlantic, built to replace the ones already sinking. The mathematics of the Atlantic are brutal. In 1942, German U-boats sink a merchant vessel every 3 hours. Between January and June, the Germans destroyed 262 ships, 1.5 million tons of cargo. The loss rate reaches 900,000 tons per month. This is not a supply problem. This is an existential crisis. Without cargo ships, Britain starves. Without cargo ships, the invasion of Europe becomes impossible. Without cargo ships, the United States cannot fight a two-front war. Roosevelt understands the calculation. He addresses Congress on January 6th. He will build not 200 ships, but 8 million tons of shipping capacity annually. The number sounds invented. The shipyard directors laugh. It is impossible. The problem is not steel. American mills produce 86 million tons yearly. The problem is not labor. 500,000 workers are already employed in shipbuilding. The problem is time. A Liberty ship takes 240 days to build using traditional methods. Riveting, sealing, testing each joint individually. A riveter can complete 10 rivets per hour. A cargo ship requires 250,000 rivets. The mathematics are unforgiving. To build 8 million tons of ships per year requires completing 1 Liberty ship every 2-4 days. The current method will never achieve this. The bottleneck is riveting. The riveted joint is a technology inherited from the 19th century. It is slow. It is unreliable. It is obsolete. But the Navy has no alternative. Rivets work like this. A worker heats a steel rivet to 2,000 degrees Fahrenheit. A second worker inserts it through overlapping steel plates. A third worker uses a pneumatic hammer to flatten the tail. The joint seals under pressure. One ship requires a team of 100 riveting squads working for weeks. Each rivet that fails weakens the hull. Each rivet that leaks means water inside the cargo hold. Water inside a Liberty ship means 10,000 tons of supplies on the ocean floor. In 1942, the Navy understands that welding exists. Welding is faster. A welder can fuse 2 pieces of steel in seconds. No rivets. No 3-man teams. No heating cycles. 1 man, 1 torch, 1 continuous joint. But the Navy has never seen a welded ship survive combat conditions. Welded joints are untested at sea. In rough water, in stress, in collision, the welds crack. The hull fractures. The ship sinks. The risk is too high. The Navy refuses. So the shipyards rivet. The order comes down from Washington in early 1942. Faster production or the war effort fails. The directors know this is impossible with current methods. They hire more riveters. They hire women. They hire men over 65. They hire teenagers. The riveting workforce expands from 50,000 to 200,000 in 18 months. Workers stand in freezing air at 4 a.m. They work 12-hour shifts. They repeat the same motion 10,000 times per shift. Carpal tunnel is rampant. Hearing loss from pneumatic hammers is permanent. Fingers are missing. Men collapse from exhaustion. The death rate climbs. In 1942, 71 workers die in shipyard accidents. In 1943, 142 die, mostly riveters. Falls from scaffolding, crushed by steel, explosions in the torch compartments. The production rate is still not enough. By March 1942, Newport News is behind schedule. They have 47 incomplete Liberty ships. The Navy is asking for 8 more per month. The math doesn't work. The bottleneck is clear. The riveting teams cannot move fast enough. The pressure is absolute. The deadline is impossible. The yard manager, a man named William Goff, calls a meeting. He is 56 years old. He has been building ships for 34 years. He watched the industry transition from sail to steam. He knows every constraint. He states the obvious. They need welding. The engineers reject it. The Navy rejects it. The liability is too high. But something has to change. On March 17, 1942, a welder named William Henry Hank Medina is finishing a swing shift at Newport News. He is 41 years old. He is a journeyman welder with 14 years of experience. He has drunk 4 beers during his lunch break and 2 more in the parking lot. He is not drunk. He is medicated. He is trying to quiet something inside his mind. He works the graveyard shift anyway. The overtime pays time and a half. He enters dry dock number 12. He sees a section of hull plating that needs reinforcement. The traditional method, bolt or rivet it. The plates are 5/16 inches of steel, overlapped, requiring 120 rivets across a 12-foot seam. Medina decides to try something different. He pulls on his welding gloves. He lights his acetylene torch. The flame reaches 3,500 degrees. Instead of heating individual rivets, he runs a continuous bead along the entire seam. The 2 plates fuse. 1 joint. No rivets. No fasteners. Complete in 3 minutes. He does not call a supervisor. He does not ask permission. He simply does it. The joint cools. The metal contracts. It holds. March 18, 1942. 6:15 a.m. Newport News Shipyard. Quality Control Office. The morning shift supervisor, Lieutenant Commander Robert Morrison, receives the report at 6:15 a.m. A welder has welded a hull section instead of riveting it. This violates every protocol. Welding on Navy contracts requires written authorization from the Bureau of Ships. There is no authorization. There is only a continuous bead of steel running 12 feet across the hull of a ship owned by the United States government. Morrison is 48 years old. He is a former Navy engineer. He has 22 years in shipbuilding. He knows the rulebook. He also knows that the rulebook was written for peacetime. The war is not peacetime. He walks to dry dock number 12 with his chief inspector, a man named Clarence Fulton. Fulton is 61. He has inspected riveted joints for 41 years. He has rejected thousands of them. He knows what a weak joint looks like. He knows what pressure failure looks like. He has seen it on ships. They examine the welded seam. The metal is clean. The bead is uniform. The penetration is complete. Fulton runs his hand across it. He taps it with a hammer. It does not crack. It does not flex abnormally. Fulton says, "It's solid." Morrison asks, "How long did it take?" The answer, 3 minutes. A comparable riveted joint takes 18 minutes minimum. The difference is a factor of 6. If this method works, if it holds, if it scales, the math changes completely. A Liberty ship could be assembled in 40 days instead of 240. The production target becomes mathematically possible. But there is a problem. This violates contract specifications. The contracts specify riveted construction. The Navy has rejected welded ships because welded hulls have never been tested in extended ocean service. No one knows if a welded hull will hold under the stress of a North Atlantic storm. No one knows if a welder's mistake, a cold joint, incomplete penetration, porous metal, will cause catastrophic hull failure. Morrison makes a decision. He documents the unauthorized weld as an experimental junction. He does not order it removed. He does not report it to the Navy. He calls the chief engineer of Newport News, a man named William Shea, March 18, 1942. 7:40 a.m. Chief Engineer's Office, Building 47. William Shea is 52 years old. He is an MIT-trained structural engineer. He has designed 3 cargo ships already. He understands both riveting and welding. He has studied the theoretical advantages of welding. He has also read the Navy's rejection letters. Morrison shows him the photographs of the weld. He shows him the inspection report. Shea does the calculation in his head. If welding works, if the Navy accepts it, production increases by 600%. The shipyard becomes critical infrastructure. The workforce doubles. The prestige becomes national. Shea also calculates the other outcome. If a welded ship fails in combat, if sailors die, if the wreck is attributed to poor workmanship or negligence on his watch, his career ends. The shipyard faces criminal charges. The Navy bans all contractors from future work. Shea says, "We need 10 more samples. Different conditions, different welders, different joint configurations." This is March 18th. The Navy expects progress reports by April 1st. 13 days to prove that welding can work. March 1930, 1942. Dry dock numbers 8, 9, 11, 12. Experimental phase. Shea assembles a team. The lead welders are Henry Medina, the man who started this, and 4 others. Thomas Rizzo, 36 years old, Marcus Webb, 28, James Kowalski, 44, and a younger man named David Chen, 24. None of them has formal welding certification. All of them learned welding through apprenticeship and repetition. All of them understand metal instinctively. The tests begin. The engineers require different joint types: flat seams, vertical seams, overhead seams, corners, T-joints, cruciform joints. Each configuration presents different challenges. Gravity works differently. Heat distribution changes. The risk of defects increases. Medina performs 34 test welds. Rizzo performs 41. Webb performs 28. Each weld is sectioned, cut in half, and examined under magnification. The engineers look for porosity, cold joints, incomplete fusion, cracks in the heat-affected zone. The results vary. Some welds are perfect. Some have minor defects. A few fail catastrophically when hydraulic pressure is applied. Shea recognizes a pattern. The quality depends on the welder's technique, the ambient temperature, and the exact composition of the filler material. In March, Hampton Roads is still cold. The steel plates are below 50 degrees Fahrenheit when welded. Cold steel absorbs heat differently. Cracks form more easily. On March 26th, an engineer named Dr. Harold Foster suggests preheating the steel plates to 150 degrees Fahrenheit before welding. Foster is 41 years old. He has a PhD in metallurgy from Carnegie Institute of Technology. He has never worked in a shipyard before. He was hired specifically to solve this problem. The preheating changes everything. The next 20 welds are flawless. Porosity disappears. Cold joints vanish. Shea understands. This is not about whether welding works. Welding already works. This is about standardization, process, repeatability, control. By March 30th, the team has 147 test welds. 133 of them are classified as acceptable. The failure rate is 9.5%. For riveted construction, the rejection rate is typically 4%. The welding process is still inferior in terms of reliability, but Medina and Foster propose a solution. Train the welders more carefully, implement the preheat procedure, add quality inspections at every stage. They calculate that this will reduce defects to 3% within 2 months. Morrison submits the report to the Navy on March 31st. The Navy responds on April 2nd. Conditional approval for 10 welded ships as a pilot program. The ships will be tested under stress. If they hold, welding becomes standard. Shea meets with the team on April 3rd. The message is clear. Failure is not an option. The welds must hold. The ships must perform. The industry must change. Medina nods. He knows what this means. He is no longer a drunk man welding in the dark. He is an engineer. He is part of the solution. The work accelerates. April 15th, 1942, Norfolk Naval Station, Virginia. The first welded Liberty ship slides down the launchway into the Atlantic. Her name is USS James Farley. She is 441 feet long. She weighs 10,500 tons. She is a prototype. Every weld is documented. Every seam is marked. The Navy has assigned a team of engineers to monitor her performance. Her maiden voyage is not a combat mission. It is a test run to Baltimore and back, a distance of 240 nautical miles. The ocean conditions are moderate. The sea state is 4 feet. The wind is 12 knots from the northeast. The temperature is 54 degrees Fahrenheit. Captain Edmund Hayes commands the vessel. He is 51 years old. He is a merchant marine captain with 27 years at sea. He does not trust welding. He has seen riveted ships survive storms. He has never seen a welded ship survive anything. He brings his chief engineer, a man named Robert Pearson, to inspect the welds personally before departure. Pearson is 48 years old. He has 19 years in merchant service. He climbs into the cargo hold with a flashlight and a small hammer. He taps along the seams. He looks for visible cracks, cold joints, surface imperfections. He finds none. The welds are clean. The penetration is consistent. Pearson tells Hayes, "The welds are better than some of the riveted work I've seen." Hayes replies, "Let's see if they hold when we hit rough water." The USS James Farley leaves Norfolk at 600 hours on April 15th. She carries 8,500 tons of cargo, ammunition, machine parts, and 240 tons of flour for Britain. The departure is documented. The media is present. This is a propaganda moment. If the ship fails, the failure is public. The crossing takes 36 hours. The weather remains moderate for the first 18 hours. At 0200 hours on April 16th, the barometer drops to 28.6 inches. A low-pressure system moves in from the Atlantic. The sea state increases to 6 feet. Wind speed reaches 22 knots. The ship begins to pitch. The hull flexes. Every weld experiences stress. Every rivet on a conventional ship would be experiencing pressure cycles. The theoretical risk is real. A weak weld could fracture under cyclic stress. The chief engineer Pearson descends into the cargo hold at 400 hours. He's looking for leaks. Water inside a cargo hold means disaster. He finds nothing. The welds are holding. The seams are dry. He checks again at 800 hours, still dry. At 1200 hours on April 16th, the USS James Farley reaches Baltimore. She docks without incident. A team of Navy inspectors immediately boards. They inspect every visible weld. They search for cracks, fractures, or separation. They find no damage. The ship is unloaded. She is inspected again. The welds are intact. The test is a success. But success in moderate conditions is not sufficient. The Navy demands a stress test. May 3, 1942. Newport News Shipyard. Test tank facility. A section of welded hull plating, 40 feet long, 12 feet tall, is removed from USS Henry Clay, the second welded Liberty ship. The section is placed in a hydraulic test tank. Water pressure is applied incrementally. The engineers are measuring the pressure at which the first weld fractures. For a riveted joint of comparable size, the failure pressure is typically 180 pounds per square inch at the rivet heads. Dr. Harold Foster monitors the instruments. The pressure increases. 50 psi, 100 psi, 150 psi, 180 psi. The welds hold. No visible cracks. No separation. The pressure continues. 200 psi, 220 psi, 240 psi. At 245 psi, the first failure occurs. But it is not a weld failure. It is a failure of the steel plate itself. The metal tears apart adjacent to a weld. The weld itself remains intact. Foster repeats the test with 5 additional sections. Same result. The welds fail at pressures 35 to 42% higher than riveted joints. The welds are stronger. The Navy receives the report on May 7th. The response is immediate. All future Liberty ships will use welded construction. The pilot program is authorized to expand from 10 ships to 50 ships. June 3, 1942. Newport News Shipyard. Production begins. The change is not instantaneous. The shipyard has 340 riveters employed. None of them want to become welders. Riveting is their skill. Welding is unfamiliar. The union negotiates. Riveters will be retrained at full pay. The transition begins. Henry Medina is designated as chief welder. He trains the former riveters. The process is painful. A journeyman riveter takes 12 weeks to become a competent welder. The Navy cannot wait 12 weeks. The target is 4 weeks. Medina implements intensive training, 8-hour shifts of hands-on practice, theoretical instruction on metal properties, practical exercises on scrap steel. The washout rate is 23%. Some men cannot master the technique. Some men refuse. They request transfers. By July 1st, 87 welders are operational. By August 1st, 156. By September 1st, 267. The workforce expands. The shipyard hires men with no experience. High school graduates, farm workers, even prison inmates on temporary release. The training is compressed. 3 weeks, 2 weeks. Some men begin welding after only 10 days of instruction. The quality problems emerge immediately. July 15th, 1942. USS Patrick Henry, Dry Dock Number 7. A newly completed Liberty ship is undergoing pressure tests before delivery to the Navy. At 800 hours, water begins leaking from a seam on the port side midship. The leak is identified as a cold joint, a weld that did not properly fuse the 2 steel plates. The welder who performed this work is a 19-year-old farm boy named Robert Schultz. He had been welding for 9 days. The weld was executed at 300 hours in sub-freezing ambient temperature. The steel was cold, he did not preheat it. The weld failed. The damage is not catastrophic, but it is significant. The section must be cut out. The joint must be re-welded. The delay cost 4 days of production. The cost is approximately $2,400, equivalent to $37,000 in modern currency. Foster convenes an emergency meeting. The problem is clear: inadequate training, insufficient quality control, rushing the process. The welders are working too fast. Mistakes are multiplying. The solution: implement a 3-tier quality control system. First, the welder self-inspects. Second, a line inspector verifies every weld visually. Third, a senior inspector conducts random sectioning, cutting welds in half and examining them under magnification. The process slows production by 12%, but defects drop from 8.7% to 2.1%. By September, defects are below 1.5%. September 1st, 1942, production summary. Newport News has completed 73 Liberty ships. Of these, 47 are fully welded, 18 are hybrid construction, welded hull, riveted superstructure. 8 are riveted. The average construction time for welded ships is 62 days. For riveted ships, it is 184 days. The production acceleration is measurable. In June 1942, Newport News produced 4 ships per month. In September, it is producing 9 ships per month. The increase is 225% in 3 months. Across all American shipyards, Kaiser, Bethlehem, New York Shipbuilding, Federal, Sun, the adoption accelerates. By December 1942, 89% of new Liberty ships are welded. By June 1943, 98% are welded. The total production reaches the Roosevelt target. In 1943, American shipyards build 1,188 cargo ships. The replacement rate exceeds the loss rate. For the first time, the Atlantic supply line is secure. Henry Medina is never promoted. He never becomes an engineer. He remains a welder. He dies in 1967 of pneumonia, complicated by emphysema from decades of welding fumes. He is 66 years old. He receives no medal, no recognition. History forgets his name. But his weld, that single unauthorized bead of steel on March 17, 1942, changes the war. December 7, 1942, Atlantic Ocean, convoy SC-110. 37 Liberty ships leave Hampton Roads bound for Liverpool. They carry 185,000 tons of cargo, steel plates, locomotives, ammunition, grain. The convoy is protected by 2 destroyers and 3 corvettes. The probability that all 37 ships will reach their destination is calculated at 73%. 2 years earlier, the probability was 24%. The difference is welding. By December 1942, the shipbuilding industry has executed a complete technological transition. Riveting is obsolete in military construction. 32 American shipyards are producing welded vessels exclusively. The production rate has stabilized at 2.1 ships per day across the entire industry. This equals 767 ships per year. The calculation Roosevelt demanded on January 6th is now routine. The Atlantic War changes in response. In 1942, German U-boats sink 1,160 merchant vessels. Total tonnage lost, 7.5 million tons. The casualty rate is 15,000 merchant sailors. The food supply in Britain is rationed to 1,600 calories per person per day. Malnutrition is visible in children. In 1943, despite increased U-boat activity, the tonnage loss decreases to 3.1 million tons. The casualty rate falls to 6,100 sailors. The food ration in Britain increases to 2,100 calories per day. The margin becomes survivable. The reason is simple mathematics. In 1942, the loss rate exceeds production. Each month, more ships sink than shipyards can build. The net tonnage available for cargo decreases. The gap widens. Starvation becomes possible. In 1943, production exceeds loss rate. For every ship sunk, the shipyards build 1.4 replacements. The net tonnage increases. The gap closes. Britain survives. Admiral Sir Percy Noble, commanding the Royal Navy's western approaches, calculates that without the welded Liberty ship, Britain cannot sustain the war beyond 1944. The analysis is classified. It is declassified in 1968. By then, everyone knows the fact was true. 1943-1945. Expansion and adaptation. The welding revolution spreads beyond cargo ships. The Navy experiments with welded destroyers, welded cruisers, welded aircraft carriers. By 1944, the USS Essex, a 27,000-ton aircraft carrier built with welded construction, completes sea trials. The welds perform flawlessly. Future carrier production incorporates full welding. The technology also accelerates military aircraft production. The Douglas DC-3 aircraft requires 50,000 rivets. Production of a single airframe takes 210 hours. In 1943, Consolidated Aircraft begins experimenting with welded fuselage sections. The process reduces assembly time to 127 hours. By 1944, 34% of new transport aircraft use welded construction. The adoption spreads to land warfare. Welded tank hulls replace riveted construction. M4 Sherman tanks with welded hulls enter production in 1943. The improvement in production speed is 18%. The improvement in structural integrity is 23%. The cascade effect is measurable. In 1942, American war production indexes are at 100% baseline. In 1943, baseline increases to 142%. In 1944, baseline increases to 187%. The production increase is partly due to more factories, more workers, more raw materials. But approximately 31% of the increase is attributable to process improvements initiated by welding technology. By May 1945, Germany surrenders. The war in Europe ends. The calculation of why is complex. It involves strategy, logistics, casualties, industrial capacity, leadership, and luck. But one factor is quantifiable. Without sufficient cargo ships, the amphibious invasion of Normandy cannot be sustained. 70% of the cargo ships used in Operation Overlord are Liberty ships. 81% of those are welded. Without welding, the invasion fails. 1945-1960, industrial transformation. The welding revolution does not end with the war. The technology spreads into civilian industry. Pipeline construction becomes welded. High-pressure vessels become welded. Pressure vessels for refineries, chemical plants, nuclear reactors, all become welded. In 1947, the American Society of Mechanical Engineers establishes the ASME Boiler and Pressure Vessel Code. Section 8 specifies welded construction standards. The code becomes the global standard for pressure equipment. Bridge construction evolves. In 1946, the first all-welded steel bridge, the Arroyo Seco pedestrian bridge in Los Angeles, opens to traffic. It is 1,000 feet long. It uses 427 tons of welded steel. The construction time is 14 weeks. A riveted bridge of comparable design would require 26 weeks. By 1960, 89% of new steel structures in the United States employ welded construction. The shift is permanent. Riveting survives in specialized applications, aerospace, historical restoration, but industrial riveting is extinct. The transformation creates new industries. Welding equipment manufacturing expands. Lincoln Electric, founded in 1895, becomes a multinational corporation by 1950. Miller Electric, founded in 1929, becomes a global leader. New companies emerge: ESABE, Hypertherm, Hobart Brothers. The welding equipment industry becomes a $2.3 billion sector by 1980. Training and certification develop. The American Welding Society, founded in 1919, expands dramatically. By 1960, certified welders number 187,000 in the United States. By 1980, the number reaches 1.4 million. A skilled welder becomes a stable, well-compensated profession. 1960-2025. Modern era and legacy. Welding technology advances exponentially. Shielded metal arc welding, SEMA-W, becomes gas metal arc welding, GMAW, then gas tungsten arc welding, GTAW, then plasma arc welding, then friction stir welding. By 2000, laser welding enters industrial production. By 2010, electron beam welding becomes routine. By 2020, robotic and automated welding systems dominate high-volume manufacturing. The modern welding robot, first deployed in 1961 by Unimation for General Motors, accelerates the trend. By 1980, 15,000 welding robots operate in American factories. By 2000, the number exceeds 150,000. By 2025, automated welding systems are standard in automotive, aerospace, shipbuilding, and heavy equipment industries. The consequence is measurable. Production cost per welded joint has decreased by 94% since 1942. Defect rates have decreased from 1.5% in 1943 to 0.03% in modern automated systems. The entire infrastructure of industrial civilization is now built on welding technology. Modern container ships, 20,000 TEU capacity, are fully welded. Modern oil tankers, 330,000 tons, are fully welded. Modern bridges, skyscrapers, tunnels, pressure vessels, pipelines, spacecraft, submarines, all are welded. The total tonnage of welded structures worldwide is estimated at 4.2 billion tons annually. The economic value is calculated at $687 billion. The industry employs 2.1 million workers directly and 8.7 million indirectly. Reflection: what the accident revealed. Henry Medina never knew the name of the welder who might have discovered welding if he had not. There was no such person. Welding as a technology existed, but the courage to use it, to implement it at scale, under pressure, under uncertainty, that was rarer than the technology itself. The accident revealed something fundamental about innovation under crisis. Innovation does not emerge from committees or strategic planning. It emerges from constraint. The Navy rejected welding. The industry could not meet production targets. A drunk welder at 4 a.m. in freezing conditions made a choice to break protocol. That choice was illegal. That choice violated contract specifications. That choice risked lives. If a welded ship had failed in combat, Medina would have been prosecuted for negligence. But the weld held. The ship held. The rest followed. The historical lesson is not about welding. Welding was inevitable. The lesson is about systems under stress. When a system is failing, when the conventional approach cannot succeed, when the only path forward is unknown, innovation becomes not optional, but mandatory. It becomes the only survival strategy. Between 1942 and 1945, American shipyards built 2,751 Liberty ships. Of these, 2,710 were welded. Approximately 200 of these ships were sunk by enemy action. Another 400 were lost to weather, collision, mechanical failure, or other causes. The remaining 2,110 delivered cargo to Britain, the Soviet Union, and the United States. The total tonnage delivered 54 million tons of weapons, ammunition, vehicles, fuel, grain, and supplies. Without welding, that cargo never reaches its destination. Without that cargo, the war ends differently. Possibly it doesn't end at all. This is not speculation. This is the mathematics of logistics. This is what one unauthorized weld accomplished on a morning in March 1942. This is what happens when constraint forces innovation. This is what happens when a drunk welder changes history by simply refusing to follow the rulebook. The weld holds. Everything else follows.